So this paper is scaling deep learning for materials discovery. It's published November 29, 2023. So today is December 3, so that's like 4 or 5 days ago. It's pretty recent. And I did check out the first author is emergent, and this person is an AI resident at Google, and the rest of them at Google too. So this paper comes from Google, and a pretty this is published on the Nature Communication, which is a pretty popular one. Also have some very good breakthrough information in the paper. So first, let me go through the abstract. There's the one that read the whole thing and see what it actually is about. So for generative motivation, so the general idea is they first mention the novel functional materials. They are materials that have breakthroughs and have very advanced uh, functionalities. So for example, they have superconductivity, material have superior strength, etc. And now you can see like all kind of material evolution. The humanity evolution depend a lot on material, right? Like we change from stone to bronze and to iron. With the more advanced material, we can have more access to new technology. And today is like composite and nanotechnology. Anyways, but with all these new breakthrough materials, we can accelerate our technological advancement. And the thing about explore new material is that what we can do to explore new material is we can trial and error. So we create new material and then we test it out, see if this material works or not, if it fit our need or not. But the thing is, this approach is it's very expensive, right? We make new material with like thousands of dollars, $100,000 machine to generate new material, and also impractical. There's too many of them, and it's not very practical for us to create like billions of different material. And so what another way you can do it computationally. So you can use deep learning and give deep learning is known to give good prediction. And so we can use deep learning and we can use that to explore the new material, and that's the point. So that's the general idea. So for this paper specifically, you remember the title. The title is scaling is the keyword. Deep learning for material discovery. And with the word scaling, basically they use a neural networks model. It's called graph neural networks. They increase one order of magnitude of no stable material. So one order of magnitude means like 10 times our no stable materials. And stable just means that it doesn't decompose in like in outside room temperature. Right? And like one order of magnitude is pretty significant. That's like 10 times. Right? This is the introduction is basically just a more detailed abstract. Let's go with the more details. You have for data in the past, experimentally, we know about 20,000 stable structures. So with the help of computation, we was able to use the first principle calculation, or this is a density functional theory, DFT. It's a very popular thing, and we were able to discover like more than double, so 48,000 stable structures. However, this is in the past. With this model, they were able to uh, explore 421,000 stable structures. So that's like 10 times, right? 48,000 to 421,000, almost 10 times, the one order of magnitude. And also, they claim it's their first model that accurately predicts stability. So before the machine learning model, they're not very efficient, they're inefficient at predict stability. And this model is going to be the first model that can come up with an accurate stability approach. They first going to establish a method of generating diverse candidates. So basically, they're going to generate new material, and then that's two ways, by the way. Um, a new symmetry-aware partial substitution, SAPS, I will go into detail later, and also you can do random structure search. So now, once you generate new candidate, you're going to use graph neural network, GNNs, and then you can improve the modeling of the material properties. So you pretty much going to filter out the good candidate. And then finally, you're going to check the the results, the filter out candidate after GNN. GNN is the filter. You check them with DST, which is a pretty popular way to check it, faster way too. And here's some vocabulary you can encounter. The first one is GNN, that's graph neural network. It's a type of neural networks. And then we have GNOME, because genome is basically the name of the model of this paper. And it's short for graph networks for material exploration. And finally, in the last part of the introduction is the genome's result. So the result of this model, they are very good, very awesome, and they have very high potential applications. Now this is the next part is the important figure. Actually, most of them are not that important because it's basically so, like this model, the genome model, is simply better, is a good, better than the previous data, and that's it. But the one important figure that I want to focus on is the first figure, which explains that model. So that's what I'm interested in. So there's a summary of the genome-based discoveries of the genome model, right? So how model-based filtration and DFT serve as a data flywheel to improve prediction. You have filtration, or the filter I tell you, and then DFT is right here. It's like a check if it's a good stable or not. So now let's first, well, it's a little intimidating to look at all of them. So let's first focus on this part of the figure, and it's a structural pili. So first you have like the um, input, right? Then you can either go to one of them. So one of the options you go to structural pili, and in this structural pili, you basically you have pretty much a structure, material structure already, structural. So, and then you modify it, and the way you modify it, they modify it with symmetry-aware partial substitution. And it's worth noting that it's symmetry, right? So the structure matters, it's symmetry, and also partial. So you don't replace everything with everything else. You only replace part of it, partial. And by modify, they get about 10 to the 9 candidate, which is 100 of billions candidate. Once you get all the candidate, you use genome, which is the graph, right? Graph neural network, to filter out most promising ones. So you have a lot of them, you filter out the one that you think is good enough. So that's the structural pili. Once you have the potential one, you just put it in the aptitude check. Now, the other option was from the input. That's not the only option, right? You have another option is that you can go down here to the compositional pili. So for this compositional pili, what you get, the input is not a structure anymore. Input is a reduced chemical formula. So in this case, this is a chemical formula that is reduced. So we don't specifically care about the structure of it. We only care about like how many, what atoms are involved, what elements are involved in the chemical formulas, and how many of them. The next thing we do is we kind of relax the constraints a little bit. So, because we want to make sure it's more diverse, we don't want to restrict it too much. And with this relaxed constraint, we can have a lot of candidates, a lot of different graphs coming, different structure coming one composition. And with this graph, with this new structures, candidate structures, we use a genome, again, the graph neural networks, to filter out of them. And we're going to get about 100 structures, promising one, the one that we think is going to work. And then to test them, we use AIRSS. This is called app initial random structure searching to just checking the stability of these structures. And with the compositional pipeline, you can predict the stability of without structural information. So you don't input structure, you input a chemical formulas. Right? Now we go back to the original figure. We're going to complete the loop now. Now that we understand both of this, you have input, right? And you go through structural pipeline, so the structure at the beginning, and then you check the stability. You replace some of them, change, modify the structure. You get some candidate, use graph neural networks, and to filter out a promising one. On this row, you come up, input's going to be the reduced chemical formula, use graph neural networks to filter out, to pretty much generate the good structure, and then you check the stability with this AIRSS, and then both of them, you go to DFT to calculate, do the calculation, and this calculation go to this genome database, the energies and stuff like that, see if it's stable or not. But that's the whole point of stability, right? It's the energy. And then now it's in here, you can loop it back. Right now you have the data, the good data. You can loop it back to the input, and you continue doing it again and again and again, multiple times. And that's pretty much the base, the fundamentals of a genome. So from this genome, they were able to get 2.2 million stable structures, I guess, when it converged, pretty much. When loss function conversion is what they get, 2.2 million. And also learn a lot about the interatomic potentials of the genome database. So that's good. For conclusion, they say that was important, one order of magnitude expansion. That's a lot for stable structures. And also, is this one is breakthrough too, in the mean that there's a difference between machine learning algorithm and material discovery. So far for machine learning algorithm, if you notice, we have like autoencoder and things like that. But pretty much, it's kind of like we relate things that, well, the input and the output, they kind of related, and there's some similarity between them. So we try to use machine learning to find the patterns between the input and the output, right? However, for material discovery, you don't necessarily do that. So you can also discover the output can be completely out of phase compared to the input. So the input and output doesn't necessarily have a pattern in machine learning algorithm. In material discovery, the output can be completely different, which is demonstrated in the GNN. So we're able to diverge it. So you make a completely new structure compared to the input. Future work is application of the model. This is just a model. There's not much of an application out of it. So they're going to need to do more hand-on application, more downstream application. And also they conclude that genome is a very powerful tool that have high potential for further application. And this is my reference I used. Basically the paper in the GitHub. Thank you for listening.